The final lesson on the pulley systems and the Atwood machines is now to just add a little bit of a new twist to put the one block on a incline. Now, as soon as you see that you have a block sliding on an incline, or potentially sliding on an incline, you need to do step one. You don't even have to really read the question in detail or any details. Rotate your coordinate system, put the positive y-axis perpendicular to the plane, put the x-axis, now the positive x goes down the plane, so I would say the negative x is to the left, and then start your analysis from your rotated coordinate system, meaning put in gravity, right? So I will almost always put gravity in straight down. We talked about not having to prove the angle theta is what it is, but the angle theta will always be the angle between your mg weight force and your negative y-axis. So I'm going to erase that so we can see the theta. But draw it in and immediately identify the mg sine theta, which is now pulling down the incline this way. So even though I have the vector drawn down here, it's actually acting on the center of the block. And I don't need the mg cosine theta in this problem, it seems, but that's where it would be. And I'm going to identify all of the forces and do a complete force diagram for both objects in the problem, for both M1 and M2. And that means I'm going to put in a normal force to keep the block from sinking into the incline. I have a rope, a cable in this problem, so I immediately put in tensions, pull, never push. So please, before beginning to even write down any equations to solve the problem or to start to solve the problem, you start to solve the problem by doing complete force diagrams. So I'm going to go over to M1, and I'm going to say I have M1G straight down. So I get my 19.6 here. And tensions pull, never push. So it is going to pull up on mass 1. So now I'm confident I have my force diagrams correct. I can think about my solution. Okay. Let's go and make sure that the question we're going to answer is actually the one they are asking. So they're telling us it's a frictionless pulley. It's an ideal pulley. For us, again, we don't even think of it as a pulley. It's a solid frictionless cylinder, and the rope slides over top of it. One rope, one tension, so that's why we have the same T's on both sides. We don't need indices when we're talking one rope, one tension. We're told that the incline is frictionless, so that is why we do not need the mg cosine theta to get the force normal, because friction, remember, friction is fun. Mu times the force normal, but we do not need that here. We were given a 2 kilogram object and a 6 kilogram object, and even if they didn't tell us it was m for mass, we need to know that a 2 kilogram object is the mass that they're giving us, and we have to multiply by 9.8 to get the weight force. So we're being asked, and we're given the angle of the incline. We're being asked to find the accelerations of the objects, and notice it's going to be one acceleration. This is a coupled system. So if M1 goes up 1 centimeter, M2 has to go down 1 centimeter. And the tension in the string, and then, they added a twist. We're going to have to calculate the speed 2 seconds after the system has been released. Well, you have to figure out the tug of war, who's winning the tug of war. And in this case, M2, let me erase it so we can see the M1 and the M2 a little more clearly. M2 is going to win the tug of war because 48.2 newtons is going to win out over 19.6 newtons. So even without making any calculations, I know, we know, you need to know when you solve the problem that M2 is going to go down and M1 is going to go up. Okay? All right. So I will couple the system and uncouple rather than try it to solve it as, independent equations and unknowns. So again, to do my mathematical calculations, I'm just basically going to unbend the system, leave the numbers, so leave the 48.2, right, in there, and when I kind of unbend it and straighten it out, I get 48.2 to the right, I get my 19.6 to the left. Now my tension becomes the glue holding the system together. I'm going to couple my system, I'm going to peanut it up. So now I just have one mass. And again, the coupled system is a really nice approach. You get one equation and one unknown. I have 48.2 minus 19.6. Total mass is 2 kilograms plus 6 kilograms, 8, and then I solve for the acceleration. So I know that M2 is accelerating down the incline at 3.6 meters per second squared, and M1 is being pulled straight up at 3.6 meters per second squared. Now to find the tension in the string, we are going to uncouple, and I'm going to look at M2 in this case. I think we looked at M1 last time, so I'm going to look at M2. So I'm going to laser focus on M2, blinders on to everything else, and that is going to give me my M2 equation. I have a positive 48.2 minus tension, because the T in the pink T here is going to the left. And now notice I only use M2, so this is M2 only. And I'm using plus 36 because we said it's moving to the right. And then I get the tension in the string. It's 26.8 newtons, and if you want to confirm, you can circle up M1 and you will get the same answer as well. Okay, well, it looks like we just need to address the speed of the objects after 2 seconds, and since it is a coupled system, they will have the same acceleration and same speed because each, again, atom and molecule is moving together. So 2 seconds from being released, I think that should be let me move it up here, V final equals V initial plus acceleration times time. It's being released from rest. V initial is 0. So after 2 seconds, you will get 3.6 times 2, or 7.2 meters per second. So there you have it. We are now ready to tackle our Lesson 5 problems. So we will do these problems, talk about them in class, and hopefully you will be expert pulley problem solvers, couplers, uncouplers, and we will take a look at your solutions in class.